Hello, Brian Miller-Hicks here in my continuing series of narrated PowerPoints on engineering geology. Today on this presentation, we're going to focus on the interplay between engineering geology and civil engineering, architecture, civil design, structural engineering design. So there's an important connection to be made among all these professionals in designing and building a stable structure. Here we see a bridge crossing a river or a lake. And as you might be able to see right away, there's different foundation conditions. Foundation is one of the crucial structures, of course, in building a stable structure. And you have to have a foundation that's suitable for ground conditions. In the west abutment, we have very stable bedrock, so we can put that concrete foundation or footing right onto that stable bedrock. Move to the right, and you see there's a pile of waste material from mining. That's not good. That's not suitable material for a foundation. It's loose, not compacted, not cemented. It's got voids in it where groundwater can seep in. It can settle and is entirely unsuitable for a foundation. So what you want to do is penetrate through that bad material and put your deep piling type foundation into stable bedrock down below. Moving to the right, you want to found this pylon as you want to found this pylon through the mineways. This pylon can rest on bedrock, but to add strength and stability, you want to penetrate down through and into the bedrock it looks like 14 feet into the bedrock to give it strength, more strength. The east abutment sits at a shallow depth directly on the bedrock. Okay, so this is a simple illustration example of different foundation conditions leading to the design and construction of different types of foundations. Okay, so in a simple case for a house, you can see that we found the house on shallow footings onto stable material, whether this is bedrock or compacted soil with high density and strength characteristics. You have to have your footings on good, strong, stable, durable material which won't settle or swell or be subject to saturation and weakening by groundwater and the like. Here's a residential foundation on prepared ground. In this case, it's fill that's been turned up and compacted, or native soil that's been ripped through for the upper 3 feet or so and then recompacted to a high strength and density, typically 90% of optimum density. Is something that we're going to cover later when I talk about laboratory testing of soils. So you have a simple perimeter strip footing filled with wooden forms, and you have concrete filling those wooden forms. And importantly, reinforcement. Here you have vertical reinforcement, which ties the footing to the structure itself, and invisible, but most likely within the concrete, there is more rebar to reinforce the concrete once it attains maximum strength. Here's finished footings, again with the steel rebar sticking up out of it, which will add connection and stability to the structure of the house above it. You want to tie everything together, and of course the footings, as I've said before, are on good, solid, stable ground. Here's something that I was involved with, which was quite interesting and challenging at times. In downtown San Diego, where they're building a lot of high rises, and parking is at a premium, so many of these building owners and designers have opted to provide underground parking, which means excavating sometimes several stories below street level, 30, 40, 50 feet or so. As they excavate downwards, they will add these wooden board, or they will, let me back up. First thing they do is drill deep into the native ground until they reach the depth of the bottom of the parking garage, as it were, as designed here. And then they put in steel beams called H-beam pilings. And then as they excavate the material, the earth material away to actually dig out the space for the parking garage, they will insert wooden lagging beams. As they go down, they put these wooden lagging boards in between the pilings to provide stability as they excavate down. And when they reach completed depth, these pilings will remain. But as an interesting sideline, geologists are called upon in downtown San Diego to log or map the sidewalls of the excavation as the excavation is being brought down. Before these lagging boards are put in to obscure their vision, they can then map sedimentary structures, stratigraphy, look for indications or identify any faults which may be present within the walls of the foundation of the excavation. So this is really quite valuable to garner some very detailed and precisely mapped geologic information as excavations are being brought down. And of course, in this case, the entire foundation of the building will be founded in very firm, stable bedrock at great depths below street level. Pile installations. So piles are simply deep footings. The first step is to drill. In this case, you want to drill with a power auger, which has a diameter typically of 24 inches and 30 inches. Drill all that material out to a designated depth agreed upon by the geotechnical engineer, civil engineer, structural engineer to provide adequate support. And once the material is excavated out by drilling, a steel cage is dropped down for reinforcement. Cast concrete is then poured into the excavated boring and the steel cage. So now you have a structure of steel and concrete which provides hefty support for the structure up above. Here's a special case of engineering geology as applied to structural engineering, civil engineering, and architecture in the case of drilling a tunnel. Drilling tunnels can be very tricky, and it's crucial that good, consistent, steady geologic information is provided to tunnel designers, because there are many conditions that can be encountered when tunnels are being drilled, such as hard rock, the existence of faults. Faults can often provide conduits for water to seep through weak rock planes, and you can get failures along fault zones. This looks like it could have been a fault, so you can get water gushing along this weakened plane in the rock. Something to look out for as a geologist logging the tunnel during excavation. Other issues include weak rock that can be quite dangerous. If it's too weak, it can burst out of the tunnel walls. Squeezing ground. If you have a clay, for example, that's a high swelling clay and you're tunneling through that, as you're tunneling through it, the walls of the tunnel can actually start squeezing inwards. General stability is something you need to look out for. Water inflow, of course, water seeping into, under, and through any structure is a crucial and potentially dangerous issue. You can have failing rock and rock bursts. A rock burst is something which may occur when you're tunneling through highly densified rock that's been subjected to high confining pressures, let's say at deep depths, maybe 50, 100 feet down. This rock has been under terrific confining pressures on all sides. Now you're opening up a hole through it, so you're relieving a lot of that pressure, and the rock may respond by bursting because of that sudden release of high pressure. That rock then is free to move. That can be a potentially quite dangerous issue as well. Okay, so last slide, just a list of guidelines to build by, all the way from the California Building Code to the International Building Code. City of San Diego has issued a very good and well-documented series of maps which show geologic hazard zones and faults on a fairly detailed basis. City of San Diego guidelines for geotechnical reports, including fault investigation reports. The last one they issued was in 2018. State of California guidelines for seismic hazards. And then civil engineering guidelines for design loads, structure risk category in terms of risk by seismic events or earthquakes. Thank you for watching.